Carl Fällgren. I work at the Technical University in Darmstadt at the Materials Mechanics Group at Professor Vormwald's group. And yeah, so my presentation about today is about the evaluation of the endurance limit of notch intersections under inner pressure loadings. Here, this was a project which was funded by the Federal Ministry of Economic Affairs and Energy of Germany and the FEV Research Association and so on, but we'll get to the topic. So the motivation is that many components subjected to inner pressure loading, like here shown on the right side, which is a common rail for highly compressed diesel injection systems, or is it diesel injection system? They show intersecting holes, as you can see here. You have one main bore and you have all those crossing holes. And failure always originates from the notches at the hole intersections. And there's one method to increase the fatigue life of those components, and it's called autofritage. Perhaps yesterday you heard some brief introduction about it. So autofritage is a process which basically is a single peak overload before the component is put into operation, and that means you get plastic deformation on the inside, and what you actually get is you induce life-prolonging residual stresses into especially highly stressed areas of those components. Yes. And those compressive residual stresses, they can decelerate crack propagation, and they can also cause crack arrest. So what our research was about, it was the investigation of the endurance limit of component-like specimens made of an ultra-high strength steel. Usually for these types of applications nowadays, steels like 42 chromo 4 are used, but we chose another one. So I'm gonna, my agenda is this brief motivation I just gave you, then I'll go to the material characterization, testing of component-like specimens, endurance limit calculation, and in the end we'll have a summary. So, material characterization. We chose this kind of steel. It's an X50 chrome vanadium 531 steel. It's an high purity electroslag remolten ultra high strength steel. We made some tensile testing with the specimens shown here on the side. So we have a not super high, but we have a very high ultimate tensile strength of 2,245 megapascals. And in comparison, here just shown the 42 chromo 4, we have a ultimate tensile strength of approximately 75% higher. Yes, we also did cyclic testing with LCF samples. It was fully reversed cyclic loading, and we made quite a lot of tests, and we also had some very high strain amplitudes of 4.75%. And on the right side, you see the cyclic properties in comparison to the quasi-static testing properties for this chosen material. So then we also performed testing of component-like specimens. What do those look like? So we have this kind of specimen here, like a cross-bore specimen, and it resembles those bore intersections that you have in, for example, this common rail system. We had two specimen geometries, and we also tested different autofritage grades. So we have this geometry, which is the original geometry, I would call it. It was used in a previous project where it was tested with a 42 chromo 4. We had three different autofritage grades. It was non-autofritaged, partially autofritaged at 8,500 bars, and fully autofritaged at 17,000 bars, and this is approximately 92% of the bursting pressure of this component, which also was tested experimentally and calculated numerically. So the main difference between the two specimens we chose is the ratio between height of the specimen and the diameter of the bore. So the thicker specimen has a ratio of 2.5. The bores always were the same, and we machined out a part of the original specimen geometry to have a thinner specimen with an H/D ratio of 2. And we had also multiple autofritage grades. We had 3,000, 6,000, 9,000, 11,000, and also a fully autofritaged at 13,000 bars. If 3,000 bar really can be called autofritage is a question I cannot answer, but it also induces some kind of residual stresses. So the testing was actually performed at our partner research institute in Weimar, Germany at the MFPA. They used like a multi-sample testing rig. Our ratio was approximately 0, but due to experimental conditions, the lowest pressure was always at 5 bars. Testing frequency was 8 to 20 hertz, so they varied that a little, and testing was until 10 to the power of 7 cycles for the H2D specimens with a ratio of 2.5. And it was tested in another way with those thinner specimens. There we tested in a load raising technique. That means we tested all specimens, and if they survived 10 to the power of 6 cycles, then we increased the load and we tested again, and so on, and so we produced a lot of runouts. But it was only 10 specimens tested. So here we have the experimental results. So on the x-axis you see the load cycles to failure, which was defined as leakage or break, and the pressure range in bars on the ordinate. And here on the lowest results in green, you see those non-autofritage specimens and an endurable pressure limit of pressure range of 2,300 bars was evaluated for this steel. And for the half autofritage specimen at 8,500 bar, we had a major increase of those this endurable pressure limit to 3,528 bar. And for 17,000 bars autofritage, we only produced runouts, because in this case, actually the testing equipment was not, or the endurance limit of the testing equipment was not as high as of the produced specimens we had. So the endurable pressure range is approximately higher than 5,900 bars. For the other specimens, which we tested in the pressure raising technique, so for 3,500 bars, we had, for 3,000 bar autofritage, we had 1,650 bar endurable pressure range, and so on. And you see all those arrows indicate runouts, and here the last failure we had at 4,000, this is something above, so 4,500 was the last endurable pressure range we could achieve with a fully autofritaged thinner specimen. So now, endurance limit calculation. First of all, what does it look like when those specimens fail? So here on the left side you see a cut through the specimen geometry with those two intersecting bores and a 90-degree angle. And the failure originates, as I told you, from the notch intersections. So we have 4 cracks which are growing, and also, those cracks grow as quarter circular cracks. Now you see this kind of butterfly shape. I will get to that exactly. And they are affected by the compressive residual stresses introduced into the component after autofritage. So exactly on this bisector line we have here, the residual stresses are the highest, and they affect this quarter circular crack path and make it more like a butterfly wing shape or something. So basically the knowledge about the residual stresses along this bisector line is required to describe how, or to calculate how these specimens fail. So how do we do that? So we made some material modeling. We tried different approaches, but now I'm going to show you what we used with a Chabosh model. So what we have here are, in red, it's the initial loading curve, and what we see in blue are all the initial unloading curves for the hysteresis loops we obtained from our cyclic testing. And in green you see cyclically stabilized loops, and we use the Chabosh model to generate 3 sets of parameters, one for the initial loading curve, one for the initial unloading curve, just to describe the autofritage pressure, and then afterwards we cycled. We did it with a finite element model, which resembles a 16th of the specimen geometry, of course, for both thicknesses, and you see here this part we chose. So when you then calculate or numerically simulate the residual stress distribution exactly along this bisector angle, which I've called Xi here, you see you get very huge residual stresses. So this red line here is for the thinner specimen, H2D equals 2. For 13,000 bars autofritage, you get a compressive residual stress, which even drops after the failure origin point down to a lower level of down to even lower values of residual compressive stresses. And also this drop, as we will see soon, is what causes cracks to arrest when they start originating and growing from the notch intersection. So to calculate the endurance limit, you need to take into account that you have the crack initiation, and first you have to calculate that, and you will do it with a local strain approach. We did it with a damage parameter PRAM, which basically is the damage parameter by Smits, Watson, and Topper, but with an additional factor taking into account mean stresses by Professor Bergman. So we get a crack initiation Wöhler curve. Then you have crack propagation, so you can use linear elastic fracture mechanics with a weight function, especially used or especially designed to use for these kind of specimens that we had. With that, you can estimate if crack arrest is going to occur or not. And also, we used the yield strip model with a weight function to calculate the failure, but I'm going to focus on this estimation of the crack arrest in this presentation. So, what we see here now. On the left side, we see a graph for the specimen with a thicker specimen with a ratio of H to D is 2.5, and on the right side, we see it for the thinner specimen. On the x-axis in both graphs, you have the autofritage pressure, which was applied to the components, and on the y-axis, you see the endurable pressure ranges. What we see here now in those green filled dots, those are the test results that we received from the MFPA, and at 17,000 bar autofritage at this highest point on the left side, I've added this arrow because we could not determine the endurable pressure range experimentally. So in the next step, the solid line marked with the X's, this is our estimation for crack initiation. On the left side, you see it's below the experimentally obtained value, which is also what we expected. You also see that it's pretty close to the specimen autofritage at 8,500 bars. But if you go further down the x-axis up to 17,000 bars of autofritage pressure applied, then you see that there's a major deviation between crack arrest and the failure of the specimen. So additionally, you see marked with the diamonds, it's the method with the linear elastic fracture mechanics we used. And there you see the estimation for the endurable pressure range for these specimens. And you see it fits better, much better than crack initiation, of course. And also we use the yield strip model, and here you see sometimes it worked better, sometimes not, but that I'm not going to go into right now. But what I'm going to go into right now is, can we really see the difference between crack initiation and crack arrest? So you see this, this little mark I made around the specimen autofritaged at 11,000 bar on the right-hand side. And as I told you, these specimens, which are the thinner ones, were tested with the pressure raising technique. So we applied a load. If it survived 10 to the power of 6 cycles, then we increased the load and so on. And then we broke open this specimen. So in the middle, in the figure in the middle, you see the failure origin, and you see arrest lines of cracks that we managed to get from the experimental approach that we used.
1 minute to
Yes.
finish, please.
And on the right side, you see our linear elastic fracture mechanics approach. And if you compare, when the stress intensity factor range drops below the delta KTH value, there should be a crack arrest. So for the blue line, which I compared it to the experimental results, I calculated an endurable pressure range of 3,830 bars, and it was actually 3,500, and I calculated it for the same measured crack length. So that you see the overestimation of pressure ranges which are endurable for these kinds of specimens was only about approximately 10%, which I'm pretty happy over. Yeah, so summary, material testing was performed. We characterized this ultra high strength steel. The applicability is very good for high pressure applications, as we could show, and raise of the endurance limit of a factor higher than 2 was possible for the autofrettage specimens. And with the calculations, fatigue lives could be described adequately, crack initiation failure and crack propagation could be distinguished, and also the length of the arrested cracks for the endurance limit could be described very well with the linear fracture mechanics-based approach. I want to thank all the funders, and that's it. Thank you for your attention.